So coming back to this diagram here, they say that amount of extra force, the force after deducting the frictional force, that net force will move this object from one position to another position. So they tell us that this net force is not actually wasted. This net force and the net work done is used to produce the kinetic energy. Okay, now the force we apply not only overcome the frictional force, but it is also used to produce the kinetic energy. That is what we are going to do this part in this part of the chapter, right? Okay, so the variables involved here, they are the distance moved lah, delta x, the applied force, sorry, the net force, which is uniform from the first position to the second position, right? At first, the velocity is zero. The initial velocity is zero. The final velocity is v. So you see that actually this net force is used to produce velocity from zero velocity to the final velocity.
Okay.
So the net force is used to produce the kinetic energy, right? So I go through with you this. The small f is usually used to denote the frictional force. The work done against the frictional force is this f, the frictional force, multiplied with d. So this is the work done against the frictional force. This work done against the frictional force, we can see it is dissipated as heat and sound. Of course, on the surface of the snow, you don't hear the sound, but
Mm-hmm.
if it's on the dry surface, not only we can feel the heat produced by the friction, we can also sometimes hear the screeching sound when you drag something along the surface of the floor. So this work done against frictional force is dissipated as heat energy and sound energy.
Okay.
Okay, next one. But what about the net force? This net force multiplied with the distance moved is called the net work done. Okay, work done by the net force is called the net work done. And this net force times the distance is the amount of net work done. And what is it used for? The energy is used to increase the kinetic energy of the object. So this net work done is actually converted into kinetic energy. Next. And this kinetic energy is given by the formula Ke equals to half mv squared. It is half multiplied with the mass of the object and the velocity of the object squared, the final velocity. So how to arrive at this formula? They're going to derive the formula for you over here. So the proof is over here. Now, if you remember the equation of motion, I think this is the third, don't know, second or third equation. We have this v square equals to u square plus 2as. Okay. Now, in your textbook, the symbol that they use, the final velocity, of course, they use v square lah. The initial velocity, they don't use u, they use v naught square. And equal to 2as. 2 multiply with the acceleration, multiply with the displacement. In the book, they use displacement as delta x. So instead of writing s as the displacement, they use delta x. So this, they are going to make a delta x the subject of the formula. So the v square, this v naught move over to the other side. So it becomes v square minus v naught square. The 2 in front, you move over to the other side, become half. So it's half v square minus v naught square.
Okay.
This is a delta x. the acceleration multiplied with the displacement. Okay, so it's written here. A is acceleration, delta x is the displacement or the change in displacement, v final velocity, v naught initial velocity. Okay, so we are going to look at the net work done. It's two words here, net and work. It's two words. Net work done is given by this symbol W net, and the calculation is F net multiplied with delta x. Okay, next. Net force is, according to Newton's second law of motion, net force is the mass times acceleration, ma. It sounds familiar. Can you see that the ma here, then multiply with the distance moved? But if you pair the a with the delta x, it's the same as the a with the delta x here. So they are the same thing. So instead of writing a delta x, I'm going to replace the a delta x with half v square minus v naught square. So this a delta x, we're going to replace with half v square minus v naught square. And you expand the formula. Expand it, it becomes half mv square minus half mv naught square. Half mv square is actually the kinetic energy. Half mv naught square is also the initial kinetic energy. Right? So if you use the final kinetic energy minus the initial kinetic energy, that is equals to the gain in kinetic energy. So it means that the net work done is fully used to gain the kinetic energy, is fully converted into the kinetic energy. So this net work done converted to kinetic energy is not something that we suspect or we think, but it is proven on this side that the net work done is actually used to increase the kinetic energy.